Yeah, but I have that for you have the
Chris, let me know when you want to roll. Okay, we can drop the lights. All right, let's roll them. It's April the 4th, 2025, and welcome to the April meeting of the Ottawa RASC Centre. Welcome to all members and visitors, and a special welcome to any members tuning in from other RASC centres across this lovely country of ours. Oop. I remember how to point it. Thank you. Thanks, Chris. Just a reminder, this meeting is in a hybrid format. We are recording the meeting for posterity, and it will be available at the ottawa-rasc.ca website. During the meeting, you can use the Q&A function in Zoom if you're dialing in to ask a question of the speaker. And a reminder that chat box comments can be seen by everyone. The raise your hand function is disabled. Hello, there we go. Just want to take the moment to acknowledge that the RASC Ottawa Centre acknowledges the trust placed in us by our First Nations with their ancestral lands and skies. And tonight's agenda. There we go. Yes, this looks up to date. So we've got a lot of observations tonight. Bountiful. We actually have had some clear nights, so that'll be interesting. But we're going to kick off the first half of the meeting with Dave Chisholm's Ottawa Skies for April, and followed by our main speaker of this evening, Bob Olson, who will be talking on Sir Isaac Newton and Isaac Newton lessons. This will be followed by our Astrobits segment after the break. Richard Taylor's actually stepped up and wanted to share something that he found interesting. So we thought this would be a suitable Astrobits segment. He's our first volunteer. Thank you, Richard. Then we'll have our observation reports. As I said, there are numerous, and Richard will once again present us with his monthly observing challenges, and we'll wrap it up with our typical announcements. All right. So far in 2029, we've had 2029. In 2025, we've had 29 new members. So welcome all new members. Any new members here tonight in person? Oh, a few of them. Oh, welcome to the meeting. Absolutely. I hope you enjoy your time here. It's a great organization. And speaking to that, Andrea is going to take a moment here and introduce herself and say a few words to new members.
Thank you. Chris, would you mind going back a slide, please? Hi, so my name's Andrea. I'm the vice president of the society here in Ottawa. And I actually wanted to come back to this because if there are any new members who are joining us for the first time on Zoom, I'm wondering if you can just say hello in the chat. And we'd like to sort of meet you. And also, I think you said there was somebody new here, and I'm just going to step aside away from the mic momentarily. I will be back. So who's there? So Cliff and Martin are two new members that are here. Cliff, actually, we will probably be hearing more about. Cliff is one of the people, along with Malcolm, who did come forward as a volunteer in our society. So that's wonderful. Cliff is a new member, but he's been involved in astronomy in our area for a long time. So thank you so much for stepping forward. That's very exciting. Martin, and if anybody else is attending online, we want to hear from you. And so now you can go to the next slide, please, Chris. I want you to send me an email. That is my email, Vice President, all one word. Tell me what you are hoping to get out of your membership, and we're going to try to see if we can connect you with the people that will help. If you are somebody who is a new member and you aren't at our meeting, please email me. I want to know why you're not coming to our meetings. Are they at a bad time? Do you not know about them? Are they not accessible to you? We want to make sure that you have an opportunity to connect with our membership and get the most that you can from your membership here. I will be at the break. I'll be right outside, and I'm willing to chat with anybody, whether you're new, old, about how you would like to improve your experience with the center. Volunteers, we are making fantastic progress. Thank you to the two volunteers who came forward. I'm also hoping to get a volunteer to help us with social media. If you're a younger person who likes and uses their phone a lot, you're qualified. And so please let me know. Jim, I know later we'll be talking about Astronomy Day. Astronomy Day, if you are a new member, please come to Astronomy Day. Bring your telescope, we can help you. And lastly, I just wanted to speak about, Estelle just mentioned that she has found in our library a book called Night Watch. It's available, and I highly recommend that you start there if you're new to astronomy. And Estelle can be reached, is it during the break or after the meeting, Estelle? Yeah, so at the break, if you would like to borrow that book or any others, come and find Estelle. All right, that's all I have to say. Thank you for the time, Paul.
Thank you, Andrea. All right, moving right along because we do have a good full program tonight. Dave Chisholm, there you go, sir.
Thank you. So I will keep things moving along here. So these are the Ottawa skies for April. So the full moon is going to be on April the 13th. And the full moon has a number of different names. The lighting here isn't great. It's known as the spreading grass moon, the growing moon, the egg moon by our early Indigenous people. It is also the Paschal full moon. This is the moon that defines when Easter starts. Easter is basically defined by the first full moon after the equinox, so March the 21st. If it happens to fall on a Sunday, then it's the Sunday after that full moon. That's why Easter is so late this year. And then our new moon is on April the 27th. We have the Lyrd's meteor shower on April 22nd and 23rd. That's an average meteor shower, about 20 per hour. Dust particles left behind by comet C 1861 G1 Thatcher. It was discovered in 1861. It runs every year from April 16th to the 25th, and it peaks this year the night of the 22nd. The thin crescent moon will not pose much of an issue watching this meteor shower. Here's the sun rise and set times. The days are getting much longer. Mercury, typically it's too close to the sun to see it, but every once in a while it's far enough away from it. So the greatest western elongation, look for the planet low in the eastern sky just before sunrise on April the 21st. Venus is visible in the early evening toward the month end. Mars is visible in the evening skies. Jupiter is visible in the evening skies. Saturn is visible in the early morning toward the month end. Right now it's rising and setting with the sun. And Uranus is visible in the early evening, and Neptune is visible in the early morning toward the month end. And there's my cartoon of the month. We're not quite as brutal as that at Flow, but I know what we feel sometimes with those trees. Thank you.
Thank you, Dave. Chris, could you turn on the podium light there for folks to read their notes? Do we have access to that? I didn't notice any difference. Maybe I'm losing my. Is it? Oh, okay. I can get you to move back. All right. I'll turn it over to Bob, and he's going to tell us about Sir Isaac Newton. Oh, there. That's perfect.
Yeah, that's good. Thank you very much, Chris. I wrote this presentation while avoiding the winter down south. I was sitting under a palm tree while drinking a pina colada. Those pina coladas may explain why some of my grammar errors. Those of you who are jealous, will be delighted to know that I returned home just in time for 75 centimeters of snow. Thanks a lot, guys. I was lied to. Everyone has heard of Sir Isaac Newton. Many of you would have studied about Newton in school, so I will not give you a long list of his notable achievements and his many awards. Instead, I will focus on some of his work that is important to astronomers. This incredibly flattering painting is the image that we associate with Newton. Next slide. This painting, without his wig, is probably a truer representation of the image that he would have presented to his contemporaries. Next image. He lived from 1643 to 1727. He lived to the ripe old age of 84. And considering he lived through the time of the Black Death, this longevity does surprise me. Next image. This is one of my favorite images of Newton. The artist has included the telescope he invented, his work on optics, his explanation of the orbits of the planets and the moon, his description of gravity, his explanation for the tides, and his developments in the field of mathematics. My own belief is that Newton was the greatest scientist who ever lived. There are some who would suggest Einstein, but I think I'll stick with Newton. Although I am very impressed with Newton as a scientist, I am less impressed with Newton as a human being. Next slide. He behaved in a way that suggested he was very insecure in his position as a famous scientist. He once said, "If I had seen further, it is by standing on the shoulders of giants." This seems nice enough until you find out that it was a shot at his rival, Robert Hooke. Hooke was short and had a stoop. He was considered at the time to be the English Leonardo da Vinci. He made his own microscope and he published drawings of what he saw. Today we call the way a spring stretches Hooke's law. Any person who had the nerve to question something that Newton said or wrote was immediately attacked by Newton. And not attacked for their ideas, but attacked in a personal kind of way. The downside of this behavior for Newton was that everybody was afraid to contradict him. So the few ideas that he had that were wrong were not corrected. Next slide, please. Newton did have a rough start to his life. His father died when he was only 3 months old, and his mother remarried shortly thereafter. When his mother remarried, she shipped him off to her mother, his grandmother. I am sure he felt spurned by the family. When he was a teenager, he threatened his father and his mother, suggesting that he would burn them and their house down around them. I can remember being angry at my parents, but I do not recall considering burning the house down. Next slide, please. When he was studying at Cambridge, when the bubonic plague arrived in England. He was 22 years of age. He decided that getting out of the crowded and diseased city of Cambridge was a good idea, and he headed to the family farm about 60 miles north. The farm was called Woolsthorpe Manor and was way out in the sticks. Newton had absolutely nothing to do except ponder the world. Next slide. Let me digress for a moment and talk about the Black Death, or more correctly, bubonic plague. Humans catch the plague when they are bitten by a flea. The flea must first have bitten someone or something sick so that it can be transferred the disease from the sick to the well. It is not usually a person who is sick, but a rat. The rats carry the plague, but the fleas of the rats don't typically bite humans. They are looking for rats. The rats carry the plague, but die from the plague, and the fleas are starving. When they are starving, they will bite their second choice, humans. There are reports that before the plague strikes, there is a die-off of rats. There are fleas that live on humans, and of course, if these fleas bite an infected person, then the next uninfected person they bite will get the plague. So Newton's idea to escape the city with all its rats and 6 people was by accident a good one. Next slide. While Newton was living in the country with no distractions whatsoever, he made good use of his time, coming up with a brilliant theory of gravity and studying prisms and optics. This is where the story of the apple falling was supposed to have occurred. Next slide. He was looking at the moon and wondering about its motion. The most common question my students would ask is, why does the moon not fall on us? But Newton had already made some insights into the motion of objects. He realized that objects would travel in a straight line at the same speed unless acted upon by some force. The idea to speed them up or make them, objects keep doing the same thing unless you push on them, either to slow them down or speed them up to make them turn. So Newton asked, why does the moon circle the Earth and not fly away? At the moment, an apple supposedly fell on his head, and he wondered if the same force that caused the apple to drop also caused the moon to bend around in a circle around the Earth. This sounds so obvious now, but it was revolutionary at the time. Scientists were not even sure that gravity would travel through a vacuum. Next slide. When I whirl a ball around my head, why does it circle my head? It circles my head because I'm pulling on the string. If I release the string, the ball will not fall on my head, but fly off across the room, sort of like the sling that David used to dispatch Goliath. The moon is the same way. Without the string of gravity pulling it around the Earth, it would fly off. Next slide. Newton took this information and stated that the Earth was not round, but bulged at the equator. Gravity holds the Earth together because it is spinning. The equator bulges out a bit. If you were standing at the equator, you are 22 miles further from the center of the Earth than you would be standing at the North Pole. This is equivalent to 4 Mount Everests. Since you are closer to the center of the Earth at the North Pole, you must weigh more at the equator. He also stated that not only does the Earth pull on the moon, but the moon pulls on the Earth. He used this to correctly explain the tides in the oceans. Next slide. In 1671, Jean Richer, working for Cassini, found that a pendulum clock was 2.5 minutes per day slower at the equator than at Paris. Next slide, please. The story of the apple falling on his head has been the source of many a joke. This is one from The Far Side by Gary Larson. I used to show this cartoon to my students when we studied this topic. Believe it or not, some of them didn't get it. Okay, next slide, please. My wife cringes every time I show a formula. What this formula says is that the pull of gravity doubles if the mass of the object doubles. If the object is further from the center of the Earth, the pull of gravity, it gets less by the square of that distance. So if something is twice as far away from the Earth, it would weigh 1/4 as much. Newton calculated, he was a brilliant mathematician, the force that would be required to make the moon circle the Earth. And he calculated the force on the apple. He found this formula worked for both. His quote at the time was, "The calculations were in good agreement." We have seen his answers, and they were exact. What exactly is the difference between weight and mass? In this formula, Fg is the weight, okay, and m is the mass. If someone asks you, what do you weigh, you should answer in newtons. And if they ask you your mass, you should answer in kilograms. Physics teacher talking there. Next slide, please. Let me give you an example. If this man is on Earth and is struck by a brick, the brick is both heavy and massive. The result would be obvious. But if this man is in outer space away from a star or a planet, he and the brick would weigh nothing. What would happen if we hit him again with the brick, but it has less weight than a feather? Sadly, objects are harder to slow down with your head because of the mass, not their weight. It would cause as much damage in outer space as it did on Earth. Next slide, please. What is your weight in the space station? We have all seen pictures of people floating around and fooling with their food. You might guess that they are weightless, but you would be wrong. The radius of the Earth is around 6,400 kilometers. The space station is about 400 kilometers high, or 68 kilometers from the center of the Earth. According to Newton's law of gravitation, you would weigh 88% as much as you do on the surface of the Earth. So what is going on? You do weigh almost the same as on Earth, but you are falling and feel weightless. Objects in orbit act a little bit like this cannonball. They are falling to Earth, but they go fast enough that they will miss the Earth and circle in orbit. Next slide, please. In 1609, Kepler published his 3 laws of planetary motion. He made these calculations using the orbits of Mars as seen by Tycho Brahe. The first law is that orbits are not circles, but ellipses. The second law states that the area of these triangles, if they occur in equal time, they are the same area. This means that the closer to the sun, the faster the planet will travel. The third law states that the time to complete an orbit squared is proportional to the distance to the sun cubed. Once Kepler had Tycho's data, it took him 8 years to come up with laws 1 and 2, and law 3 took 17 years. Kepler had no idea why the planets followed these laws, but he observed that they did. Next slide, please. I think my wife has her book open now. If you take Newton's universal law of gravitation, Kepler's laws are obvious. You start with the force of gravity is equal to the centripetal force and end with the radius cubed proportional to the period squared. Next slide. Newton's universal law of gravitation works with all the planets in our solar system. Next. And the Kuiper belt. I show this slide because I always forget how far from the sun the Kuiper belt actually is. Next slide. When I say it works for all the planets, I mean almost all the planets. Mercury displays an interesting and surprising behavior. The orbit of Mercury is an ellipse like the other planets, but the axis of the ellipse is advancing as shown in this picture. The orbit of Mercury precesses around the sun. Next slide. In 1859, Urbain Le Verrier, a French astronomer, noticed that the orbit of Mercury was precessing around the sun. It was precessing 1.56 degrees every 100 years. He figured that this must be from the gravitational effect of the other planets. A great guess. But this still left 43 arc seconds unexplained. This is about 1/100th of a degree in 100 years. How anal was this guy that he noticed this incredible small distance? Okay. He then figured out that maybe the sun was not round, but flattened. The fact that the sun is flattened is true, but doesn't explain the 43 arc seconds. Then he figured maybe there was some other unknown planet affecting Mercury. This planet would need to be between Mercury and the sun, and he called it Vulcan. Maybe he was a fan of Mr. Spock. Le Verrier had already predicted the location of Neptune using the gravitational effects of some unknown planet on Uranus. but Vulcan was never found. Next slide, please. Then Einstein entered the picture with his theory of relativity and its curved space-time explanation of gravity. Newton's laws match relativity exactly as long as things don't move too quickly, nor through a large gravitational field. But Mercury spins around the sun quickly, and the sun has a monstrous gravitational field, which Mercury moves through. Plugging the data into the theory of relativity explains the missing 43 arc seconds. This was the first proof of relativity. Next slide, please. The second proof that Einstein suggested for relativity would occur during an eclipse, when the sun went behind the moon and its brightness was cut off. Einstein suggested that we would be able to see stars that were behind the sun because the gravitational field of the sun would bend the light. Scientists around the world checked for this during the eclipse in 1919. When it was found to be true, Einstein became the most famous scientist on Earth. Next slide, please. Now back to Isaac. Newton was fascinated by light in general and prisms in particular. He did much experimenting using prisms to split sunlight into colors like we see in a rainbow. Next slide. But Newton pushed the idea further by shining the split colors onto a second prism, which recombined them back into white light. He concluded from this experiment that white light was made up of all the colors. Next slide. Next slide. This dispersion of white light into colors also occurs in lenses, as they have sloped sides and act like skinny prisms. This makes it very difficult to use single lenses in a telescope, as the different colors focus at different points. Newton suggested that the amount of dispersion was exactly proportional to the index of refraction of the glass. This would make dispersion or chromatic aberration impossible to correct in lenses. Next slide. This turned out to be incorrect. By using lenses with opposite curvature and different indexes of refraction, it is possible to make the color-corrected lens. Newton was so hostile to anyone who disagreed with him that other scientists were afraid to contradict him. This really squashed the study of optics. Next slide. Newton's solution to the problem was to make a telescope with no lenses. Instead, it used mirrors to focus the light. We now call them Newtonian telescopes, and they are very popular with astronomers. Next slide, please. This is a reproduction of Newton's telescope. Next slide, please. It is reasonably easy to scale up a Newtonian telescope. This is a monstrous 30-inch Starmaster. This is the big sister of the 18-inch Starmaster that Mike Wirths donated to the club. Interestingly, Mike used to own a 30-inch Starmaster. Next slide, please. This is 12-inch telescope is my favorite Newtonian. Next slide, please. Newton is also famous, even today, because of his 3 laws of motion. They are shown in this picture, so I'll not go into them tonight. I think your high school teachers drove those into your brain. Next slide, please. When Newton was working on his laws of motion and gravity, he realized that he didn't have the mathematics needed. For you and I, that would be the end of it. But Newton just invented another branch of math, which we now call calculus. He used this calculus to solve many problems that other scientists could not. He kept it a secret so that he would be the one making the discoveries. One day, a group of scientists asked Newton what the shape of the orbits of the planets around the sun would be if they were affected by gravity. He stated ellipses. The other scientists were puzzled and asked him how he knew this. He responded that he had calculated the answer already. They then asked for him to show his work. He had used calculus but didn't want the others to know about it, so he said the calculation was at home, but he would show it to them later. He then calculated the answer without using calculus, using instead algebra. It took him 2 years. All right. When he found the answer using calculus in minutes. 9 years later, a German also invented calculus, but published the results. Newton then claimed to have been using calculus for the last few years. There is a rule in science that the first person who published gets the credit. Newton was so powerful and so famous that they bent the rules and made them co-discoverers of calculus. Next slide, please. I personally would have given the credit to Leibniz. The invention of calculus was a monstrous step in the study of physics and of science in general. Lots of people describe physics as nothing but applied calculus. If you ever watch the TV show The Big Bang Theory, you will hear many references to physics and to calculus. Next slide, please. Newton was described by his aunt as a very strange child. He was unmarried, and as far as I know, never had a woman in his life. He claims to have died a virgin and stated that women were put on earth to distract him from his true great purpose. I don't know if I go as far as Newton claimed, but I do find women distracting. Nowadays, I think we would consider him on the autism spectrum. I feel Newton's accomplishments during his life made him our greatest scientist. He advanced the study of mechanics, light, gravity, and mathematics, and these weren't trivial advances, but giant leaps. One of his contemporaries complained that if Newton kept it up, there'd be nothing left for scientists to discover. Next slide, please. Newton died in 1727 at the age of 84. This is his death mask. He spent considerable time studying alchemy. Alchemy is the producing of gold from the baser metals such as lead and mercury. Some scholars suggest that Isaac Newton's mental and physical decline in 1693 including insomnia, paranoia, irritability, might have been linked to mercury poison. His hair has been analyzed and did contain mercury, probably from studying alchemy. Next slide, please. He was buried in this modest building, Westminster Abbey, along with the English royalty. He was the first scientist buried in the Abbey. Next slide, please. This is his grave in Westminster Abbey. I like it a ton better than his death mask. I have visited Westminster Abbey and, of course, made a pilgrimage to his grave. Thank you.
Wow. That's a lot of stuff I didn't know about Newton. All right. Well, that was great, Bob. Thank you very much. That was a very detailed account, very informative. All right, we're going to move along. Bob went a bit on to warp drive there, and so he bought us some time there. So I think we'll do our next piece, which is an announcement from Jim Thompson regarding International Astronomy Day. Jim, take it away.
So for those of you who are not familiar with International Astronomy Day, it was a public outreach event started back in 1973 by the U.S. Astronomical League. The whole purpose of the event is to promote an interest in astronomy amongst the general public, and sort of by association, interest the public in science in general, which, you know, for a modern society is a good thing. So the event is a free sidewalk, what we call a sidewalk astronomy event, where local astronomers bring their equipment out literally onto the sidewalk and let the public have a look. This year's event is scheduled for Saturday, May 3rd, so it is just under a month away. The timing this year will make a very interesting Moon-Mars conjunction available for us to look at. Jupiter will be nice and prominent still, and of course the Sun and the Moon will be out. In fact, it's the first quarter moon that usually decides when the event is going to be. Is there a clicker here? Yes, there is. To give you sort of an idea of what to expect, these are some photos taken from previous years. They're a little dated. This is my son. He's now 21 working. This is my daughter. She's now almost finished high school. So they're, you know, could use some updating maybe. The balaclava on my daughter kind of gives you an idea that who knows what you're going to expect for the weather. This particular springtime, it was very cold, but other events, we get, you know, beautiful 25 degrees Celsius. So it's sort of a be prepared event, but the basic idea is volunteers come with their telescopes. You can see the big line there. And all through the day, people come by. A lot of them don't even know what's going on. They just happen to be going shopping and they see us there. It's like, oh, telescope, cool. Come have a look. And generally, you'll be amazed at how many people come up to you and talk your ear off. They have such a keen interest in what's going on with science, and it's a very enjoyable day. Just the look on people's faces when you show them even the moon through your telescope, it's very, very exciting. So that's sort of a general idea of what's going on. The time is usually around 10 a.m. for a start. The keeners like myself, who is the coordinator, tend to get there earlier, maybe more like 7 to 8 a.m. to start setting up our telescopes. It's in a small sectioned off parking lot next to Chapters Bookstore at Silver City. That's where we've been. I believe this is the 23rd year that we've been going to that spot. I invite everyone to participate in some way. You can just come as a guest, you know, bring your kids or your grandkids, whatever, just to check it out. You could volunteer either with a telescope or just yourself to walk around and help people, you know, when somebody else needs to use the washroom or whatever, to answer questions and such. If you're interested in participating, contact me. That's my email address up on the slide there, topjimmy@rogers.com. And there's also a website that has some more background information, astrodayottawa.weebly.com. Thank you.
Thank you, Jim. We'll cross our fingers for some clear skies that day. I think we're owed some. It's been a kind of a marginal winter for that. All right, we've got time, and so we're going to jump ahead a little bit before the break. And as I mentioned, Richard Taylor is going to do an Astrobit segment tonight, and he's going to tell us about the potential for carbon dioxide geysers on Mars.
Oh, thank you. Welcome. So this is a little story about spring on Mars. I was visiting Montreal a couple of weekends ago, and I noticed that the planetarium in Montreal was having a special presentation called One Day on Mars. So I thought I'd check it out to see what it was. I haven't been to that planetarium before, so it was fairly nice. As a planetarium usually is, you get a chance to see the stars during the day, and they had a pretty good projector. It was working pretty well. But as I anticipated, I've had a lot of familiarity with Mars. I keep reading articles about it and everything. So the presentation about Mars wasn't very surprising to me until just near the end. And the presenter suddenly mentioned and showed an artist's impression of carbon dioxide geysers on Mars. So I came home and immediately started researching this because I'd never heard of these before. And yeah, it turned out to be quite true and quite interesting. This is a particular picture that sort of gives a good impression of what it looks like. There's actually holes on Mars, generally in the South Polar region, and they spout out clouds of carbon dioxide and dust. Now, these happen in spring, so it's actually driven by the sublimation of the carbon dioxide in the southern ice cap. And the other interesting thing that I found was that they are associated with something that I actually had heard of before, spiders. Well, these are not, live spiders, but they look a bit like spiders. They're little features on the surface of Mars with a dot in the middle and legs coming out of them. And that's also very strange. How did these get associated with the geysers? So these are the pictures that I remember seeing before. The spiders, as you see, let me just see, over here, are these strange topographical features that look like a blob with lots of legs coming out of it. And then there was something else that was also spotted quite a long time ago, back in 1998, dark dune spots. Black spots on the ice of the southern polar cap. So I hadn't heard that this had actually been resolved into a combined image where you see both the black spots and the spiders and definitely plumes of material that have seemed to be coming out of it. Now, Hugh Kiefer, the US Geological Survey, had actually published a paper back in 2006 explaining how this might work. This was a bit of a hypothesis rather than proven, but they figured out that this kind of combination of the spiders and the black dots were caused by carbon dioxide jets coming up from underneath the slabs of carbon dioxide ice in the South Polar Cap. What they proposed as their hypothesis was that the ice cap itself forms a kind of impermeable layer. It's translucent, meaning that it lets light go in, but just as here on Earth, carbon dioxide is opaque to infrared. So the heat from the light shining on the surface stays underneath and sublimates the carbon dioxide gas, makes a high pressure underneath this slab. And just like in a volcanic region here on Earth, when something evaporates underneath the rock, it bursts out and produces these eruptions or geysers. The interesting thing that forms the spiders is that because it's a mixture of carbon dioxide and sand grains, basically, when it produces this high pressure and then releases it all of a sudden, it comes out through channels. And those spider legs are actually the channels where the carbon dioxide has been flowing and carrying the sand away. Now, as I say, all of this was hypothesis, but what has happened very recently, last September, was the publication of experiments that have actually shown this happening in a simulated environment here on Earth. So I found this paper, and it's really quite a fascinating read. It gets a bit long and technical, but it actually shows how they set up a simulation of the Martian environment in, do I have a picture of it? No, I don't think I have a picture of the device itself, but there's an oil barrel-sized container that is depressurized, filled with a very small amount of carbon dioxide and cooled down to Martian winter temperatures so that the carbon dioxide actually starts coming out as frost. And these are pictures from inside the simulator where they actually see frost forming. It's not so clear in this first picture, but carbon dioxide frost is actually forming here. And then with heat from below, it bursts out through little black vents, just like we see on Mars, leaving behind spider-like patterns. So we now know for sure that the Kiefer model is actually true. It's actually happening in this way. The only thing we haven't seen happen is the heat forming from the sun. In the experimental version, they actually put in an artificial heater underneath the surface. On Mars, we expect it's the sun shining through the CO2 ice that warms up the dark sand and carbon dioxide underneath to sublimate it and then release the pressure. So the only thing we have left to do now is either simulate the effects of sunlight or go to Mars and actually see one of these things in action. I think that's my choice. See you there next spring. Thank you.
Thank you, Richard. Okay, just checking my time here. Sorry? Oh, yes?
Does it stay in the atmosphere? Does it condense in the winter? Does it drift off into space?
Well, you see, most of the atmosphere of Mars, sorry, the question is what happens to the carbon dioxide after it sublimates? Well, this is an ongoing process on Mars because most of the atmosphere of Mars is carbon dioxide anyway. So the big difference between the Earth and Mars in winter is those polar caps are not coming down as snow, they're building up as frost. The carbon dioxide in the atmosphere gets so cold and the surface gets so cold, you get this layer of frost forming on the ground, and it's carbon dioxide frost. So as I say, in the springtime, it starts to warm up and turn back into gaseous carbon dioxide, refilling the atmosphere basically. But it doesn't happen smoothly the way it formed in the first place. Instead, it forms under the crust and bursts out. And that carbon dioxide then just replenishes the atmosphere. Okay? Any other questions? As far as I read, I didn't see anything about the water vapor, but this may be the reason why the South Pole it seems to have these more prominently than the North Pole. I think maybe that the conditions at the South Pole are a bit colder and carbon dioxide is more prominent there. But I'm sorry, I don't know what the effects of adding water to the mixture might be. There is a definite difference between the North Pole and the South Pole with respect to these CO2 geysers. The South Pole has more of them, the North Pole doesn't. But I haven't read anything that I've seen to explain if this is a combination with water or not. Any others? Yep. Yeah, I can.
Yeah, sure.
The carbon slab is the question. This is what happens when the frost, the CO2 is starting to change from gaseous into solid. It starts out by mixing with the sand, the soil of Mars. And so it's a mixture of sand and carbon dioxide ice. And then as all of that, all the gaps in the material are filled in, then the top layer is more and more pure carbon dioxide. And that forms a hard layer. When it starts to sublimate again, as I've said, the light is coming in, shines through the carbon dioxide layer that's more pure, hits the sandier region, and that absorbs the light and changes it into heat, which sublimates the carbon dioxide that's mixed with the sand. And then you build up this pressure underneath the more pure layer of carbon dioxide that's on top until it's not very strong. It's just a crust of ice, basically. So at some point, that high pressure gas underneath will burst out and then forms these geysers. Okay. Thank you.
Okay, I think what we'll do is, given our time there and just trying to be cognizant of what we have in the second half, I think we'll have our bio break now. Time for a stretch. We can probably go a little bit longer, let's say 10 minutes, and then we'll resume with our program. Thank you. Oh, one further thing. The books on the table here, in fact, all the items on the table here are giveaways tonight. So first come, first serve, no stampeding, no pushing, no shoving. Be kind to one another, but help yourself. Thank you. Go sailing, I know. Yeah. Summer's not bad, but winter can be. But I'm an optimist, right? Yeah. Kind of like. You're not, yeah, that's right. Like the, oh man. That car, yeah, that's racist. Now you're asking too much, right? Yeah. So how's that sound? Well, I know, I've seen that coming. Not a good scenery. Yeah. You do? Yes, sir. How are you? Hi. Good. Thank you for everything. Oh, good. I have for your email. Okay. Looking. I'm definitely looking. Yeah. I don't know. Yeah, absolutely. Yeah, no, I appreciate that. I was actually going to make a verbal announcement. I put it on the camera that I put out. So yeah, no, definitely. Yeah, yeah. So I'm trying to schedule summer. Sure, yeah. Yep. I'll let people know. No problem. All right, if I could have you take your seats there, we'll resume. Thank you, Chris. All right. I won't, oh, sorry. Did you do that or did I do that? Here, I'll come back. All right, so just before we proceed with the remainder of our program, I just want to list a few of the things that we offer as our club, the benefits of our club there, especially for new members. You may not be aware of all of these goodies, but being a member of the club entitles you to a number of rather nice benefits. One of the best being the ability to engage with folks like yourself who have similar interests, and it's a nice way to get together and share those interests. We also have the Ted Bean Loan Library. That's a telescope loan library. So if you don't have a telescope but have been contemplating getting one, we can set you up with a Ted Bean Loan Library. We loan out these instruments for free, and it gives you a chance to try before you buy. So a good idea. All right. Ottawa membership goodies. Certainly we have three notable publications that come with your membership. The Observer's Handbook is a classic publication of the Society. It's been published for many decades and is still, even in this age of internet, I find that I use this book a fair bit there because I find it actually quicker to access certain types of information that I want using that. It's just chock full of good stuff, articles as well as data, and it's yours with your membership. The journal is a bi-monthly publication, bit of on a higher end, talking about a diversity of topics such as imaging and just general astrophysical topics. And then we have our monthly Astronotes, which gives you a summary of the things that we've covered in the month there, and there's also a venue for publishing your photographs if you've submitted some, if you wish to have them in the Astronotes. I think I'm zapping the ceiling. Here we go. Your membership also entitles you to the access to the Discord servers. This is for members only, and is an online meeting place where we can share ideas and ask questions. You also get you can also get a membership into Astrophysics Astrophic Pro, which is you can get a free version of this online, which is basically cloud summary and temperature summaries. It gives you a heads up, kind of like the clear sky chart, but with different levels of data as well. And the Pro version, which is available for non-members for the general public at $66 a year, enhances those features with more data. A very useful tool for planning your sessions there. That is available to you free as part of your membership. All right. The membership itself runs at $113 for a regular membership, $107.50 for a family membership, where you want to include an additional adult or youth, and you can see the prices there, 15 and 9 respectively. We also have a youth membership for students and such, under 21 years old or under 25 if you are a student, and that comes in at $72.40. So value for your money for sure. All right. Just before I proceed with this, Majid came up to me actually during the meeting and is looking for people that shot images of the lunar eclipse. He's looking to do a project measuring distances and such, and he's interested in doing a collaborative effort with anybody that has pictures that they're willing to share that have some accurate timings with them as well. There, if you wish to talk to Majid, you can reach him at majidnaji@gmail.com, and it's MAJEEDNAJI@gmail.com. And he's looking to assemble this data and do a presentation in the next little while to push out that data and see what he can derive from that. So please feel free to contact Majid if you feel like you'd like to help him out. Yes, it is MAJEEDNAJI@gmail.com. He's especially interested if I believe you were out of province, Andrea, no? For the lunar. No? Okay. He's looking for, especially for people that are more of a distance from Ottawa. I think Majid, you already mentioned that you have some imagery from close to the Ottawa area. So if you're at some distance, that provides a longer baseline to make more accurate measurements. He certainly would love to hear from you. Oh, you'll be here afterwards? Okay, Majid said he would wait at the front there at the end of our meeting. And if you're interested in contributing, please feel free to talk to Majid. There's a thought, Majid. You might want to contact the Montreal Center and see. I'm not sure what kind of weather they got for the lunar eclipse, but that would give you a longer baseline for sure. Or even some of the other centers. They're easy to connect to. Okay, so our time isn't too bad. We've got presentations, and I did have this second Astrobits segment planned. Wasn't sure whether I was going to show it, but we've been moving along pretty good on the time. So I will go through this. This is a piece that I've been mulling over for the last little while. So this segment stems from an intriguing paper by Andrew Tompkins, Aaron Martin, and Peter Kaywood, published in the Earth and Planetary Sciences letters in their October issue just passed. And it examines an interesting possibility. But first, a bit of background. Our explorations of the solar system, both with manned probes and robotic probes, huge ground-based and space-based telescopes over the last 50 years has shown us that ring systems around planetary bodies are much more common than were thought even just 50 years ago. Back then, Saturn was really the only planet known to have a system of surreal-looking rings orbiting around it. Now we know that all the gas giants in our system have rings. None, of course, as spectacular as Saturn, but they have them nevertheless. And perhaps most surprisingly, we've learned that even minor bodies, such as asteroids, can possess a system of rings. Who would have thought? So what are the possibilities for a planet like Earth? Well, Our crewed expeditions to the moon and extensive explorations by sophisticated robotic craft have returned samples for analysis, allowing us to hone our theories of how our planet comes to be orbited by such a relatively large natural satellite. While there are several theories regarding the moon's formation that are still around, nowadays it's widely believed that in the very early stages of Earth's history, our planet received a glancing blow by a Mars-sized planetesimal, basically just sideswiping it, that tore a large amount of material from our young world. If true, such a collision would most certainly have formed a ring of debris around our planet in that very ancient time. But we're talking about a time there where the Earth was still in the process of forming, probably on the order of 4.3, 4.2 billion years ago, so very early in its history. And that ring that was torn off by this glancing blow eventually coalesced to form the moon that we see in our skies today. Interestingly, recent research, if I'm getting my buttons right here, there we go. Interestingly, recent research also suggests that Mars, one of Mars's moons, Phobos, may be locked in a cycle where over millions of years, it alternates between a ring of debris orbiting the planet and a moon formed by the subsequent coalescing of that material. How would such a cycle operate? Well, Mars' gravity not only keeps the moon in its orbit, but it also creates stress in that moon and creates some of the fractures that we've actually imaged by robotic probes on that moon's surface. Over time, Mars's gravity pulls the moon in closer, bringing it within the Roche limit, the minimum distance at which a smaller body like a moon can exist as a singular object under its own gravity. Any closer, and Mars' gravity rips the moon apart, raising and raining meteoroids down onto the planet's surface, with the rest of it forming with the rest forming a ring of orbiting debris. Then, over tens of millions of years, that debris clumps back together into a new, smaller moon, and the cycle repeats. Current analysis indicates that in about 50 million years from now or so, Phobos will once again creep to within the Roche limit and be torn apart. And the research, that recent research indicates that this cycle may have repeated itself anywhere from about 3 to 5 times in the last 4.2 billion years. Interesting proposition. So back to Earth. The paper by Tompkins that caught my eye deals with a much more recent event, beginning in the Ordovician era, some 460 million years ago. It stems from geophysical studies of 21 impact craters, all believed to have been created within a relatively short window of time, geologically speaking. This chart shows those craters, lists them, and their sizes and their estimated ages. Also shown, the blue line graph in behind the horizontal lines is the Earth's average global temperature during that period of time. Excuse me. Note the pronounced dip between 465 to 435 million years ago. This is known as the Hernantian global icehouse period, and I'll have more on that in just a moment. Anyway, this enhanced period of impact cratering has been known for quite some time, for a number of decades, and it's referred to as the Ordovician impact spike. The beginning of this period is marked by a sudden increase in L-chondritic meteoric and micrometeoritic material recorded in global limestone formations all over the Earth, starting at about 466 million years ago. Together with the impact spike, this has been suggested to be the result of a breakup of a large L-chondritic type of asteroid in the asteroid belt. This would have sent fragments and clouds of asteroidal dust in all directions, and especially into the inner solar system, with a number of those fragments eventually colliding with Earth. what I felt was a remarkable work of insight when I read this paper. The study done by Tompkins and his team revealed an interesting and previously unknown correlation. In essence, they used the 6 latest models of plate tectonic movements, and they rolled back the clock. They rolled back time to see how the land masses of Earth were oriented at the time of those impacts 466 million years ago. This map of Earth shows the location of the major continental blocks at the time, and also shown are the colored dots, as the colored dots are the locations of the studied Ordovician impact craters. Note their alignment with respect to the coordinates, background coordinates of the map projection. Most of the impacts occurred on 2 continental blocks named Laurentia and Baltica. These are the ancestors of modern-day North America, Scandinavia, and Central Europe. Both of these ancient blocks were close to the equator at the time of the impact interval. These factors are a little bit better to see in this close-up view. The team then conducted an extensive statistical analysis to determine the probability that this crater creation and its distribution and alignment could just be a random occurrence. They reasoned that if the previous theories of asteroid fragments from a breakup back in the asteroid belt independently coming in on orbits from the asteroid belt were correct, then you would expect a much more random distribution of these crater impacts. And don't forget, they analyzed 21 different craters. That's like 10% of all the known impact sites on Earth, and that occurred within a 30 to 40 million year period, which again, as I say, it was geologically quite short. So their statistical analysis, and they looked, the details are in the paper. It's quite fascinating to the level that they went to try to determine this. But long story short, the analysis indicated that the odds of that occurring in this time frame with that alignment were about 1 in 25 million. They therefore proposed that just a single, and this is the crux of the paper, that just a single large chondritic body from the asteroid belt found its way towards Earth. This resulted either from a collision in the asteroid belt or from another, from a number of other mechanisms that we know operate, gravitationally speaking, in that region that actually continuously fling asteroid fragments from the belt in towards the inner solar system. In other words, a collision wasn't required. It may have been a collision, but one body, they're seeing one body coming in from the asteroid belt. That body made a near miss in their supposition. That body made a near miss to Earth, encroached within the Earth's raw-RASC limit, and fractured. Those fragment orbits, those fragments would have orbited in a number of different planes inclined to the equator, but over time, interactions between the particles, in other words, little collisions between the particles, give them enough time, and they tend to flatten out the trajectories, flatten out the orbits. Also, Earth's equatorial bulge, and Bob mentioned that in his talk with Newton, it creates a gravitationally controlled preferred orbital plane, which gradually brings these fragments, even if they're orbiting like this, gradually brings them towards a match with the equator, similar to the rotational axis of the Earth. They would then, let me see, excuse me. Well, once this ring formed like this, and these particles leveled out, basically forming a ring, much like Saturn's in the rotational plane of the planet, these fragments, especially the larger ones, would start to deorbit and encounter the Earth. So their theory goes that these fragments The larger fragments that we were looking at here, they would gradually deorbit, and over a 30 or 40 million year span of time, they would impact on Earth. And as you saw from their diagram, from their analysis, it was like, for those of you familiar with impact cratering on the moon, or if you've ever seen this, there's a number of sites on the moon where we see boom, 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 boom. We see craters in a line that we believe originate from a body fragmenting or have been fragmented before the collision, raining down on a straight line. Similar type of analogy here, except that the body is breaking up the body broke up in orbit. The particles' orbits were gradually aligned, and then those those fragments started to deorbit, enter the Earth's atmosphere, and impact on our planet. The interesting thing too is that remember I mentioned the global average temperature of the Earth. This is an interesting adjunct to the theory. They speculate that if such an equatorial ring did exist, the axial tilt of the Earth relative to the sun would cause it to partially shade the winter hemispheres on Earth, and thereby decrease the temperature gradient from the pole to the moon, or from the pole to the equator. Dust in the atmosphere produced by these impacts would also have contributed to an overall cooling, which is known to have occurred in that precise period. Such a global cooling could be explained by the presence of a ring around the Earth in that period of time, less than 500 million years ago, certainly a much more recent event compared to the formation of the Earth and the subsequent formation of the moon over 4 billion years ago. And interestingly, there's a depiction of a ring. Various artists' depictions show it at different distances, but you can see how it shadows from the ring as they do on Saturn. For those who have observed Saturn through a telescope, you'll notice that the rings cast a distinct shadow on the ball of the planet. Same would have been the case here. So it's an interesting link. And just one final note: the Brent crater up in Algonquin Park is one of the impact sites identified in this study and studied, and it may well owe its existence to a ring that was once around the Earth, and not that really long ago. Interesting work. Yeah, I recommend reading the paper there. It's if you like statistical stuff, if you like physics, and you like to see how all these things combine together, the paper is a very interesting read. All right. Observation reports. We got lots. So I ask folks to be cognizant of the fact that we've got nine folks with lots of very nice images to show. You're laughing, Oscar, and I know why you're laughing, because I'm one of those people that's guilty of going on sometimes. But yes, please be brief with your explanations, and that way that way we won't be here till 11 o'clock. Come on down, Bob. You're first on the list. I know you don't want the clicker. I'll leave the clicker for you.
Oh, could I have the lights though?
Yes, could we have the podium lights, Chris, please? I know, I needed them too.
Not yet. Yeah, please.
Oh, yeah, go. Podium light.
Lucky for you guys, I'm a Nighthawk.
It's coming. I think it's coming. Is it
Oh,
coming?
yeah, I think so.
I don't know.
The
We had
pin,
it before.
the Pinwheel Galaxy is located about 21 million light years away, It is about twice the diameter of our own Milky Way and contains roughly 100 billion stars. It was discovered by Pierre Michin in 1781 and was included that year as the 101st entry in Messier's catalog. Next slide, please. This barred spiral galaxy is about 30 million light years away. It's about the same size as our own Milky Way. When first discovered by Herschel in 1784, he thought it was a nebula. It wasn't until the 19th century that the third Earl of Rosse noticed its spiral form. That's it.
Thanks, Bob. Sorry about the lights. There you go.
Hi, everyone. I just have a couple of images this month. I'm catching up on, I think this was February's observing challenge. The title has disappeared, so I'll have to tell you what this is. We've got, no, there was meant to be a,
Oh,
is it? It's okay. So we've got, let's see. Oh, there it is. Thank you. So NGC 2282 was the challenge. And this is a little tiny reflection nebula up here. So I took this in narrowband, so I knew that I wasn't going to get much of a reflection nebula, but in any case, it popped out there. This little nebula is about 5,000 light years away, and it also has a tiny little cluster of about 100 young stars in there, about 5 to 10 million years old. What else have we got in here? There's a nice open cluster here. This is NGC 2301, and that's one of Herschel's discoveries, discovered in 1786. That's a little bit closer, about 3,000 light years away. And then the thing that really popped out when I took this image and made me put a little bit more effort in is this big patch of nebulosity down here, which is Sharpless 284 nebula. So this is quite a bit further away, 20,000 light years away. And then we're looking in Monoceros, so this is away from the center of the galaxy. So this has been subject of a little bit of study because it's unusual to find such a nice hydrogen emission nebula away from all of the disturbances of the center of the galaxy. So this has a lot of young stars, and I think they've been using it to study as a analog of earlier in the universe or the galaxy formation. You've got undisturbed nebula with some young stars. So next one. And to be a little bit more familiar, the Rosette Nebula was another one of February's challenge objects. This again is in SHO narrowband. So if we don't know about the Rosette Nebula, it's about 5,000 light years away. It's large, about 150 light years in diameter. And it's a nursery with a lot of young stars. You've got a nice central star cluster with very, very bright stars that are pushing all of this gas out the way, so much so that you even have sort of a void right at the center of the nebula where these stars have just pushed all that gas away. So quite a nice thing to image. So I think that's it for me. Thank you.
Thanks, Tony. Very nice work. Stephen Montgomery comes to us online.
Evening. So just a DSLR image, non-guided, of the lunar eclipse.
Hang on a sec, Steve. There we go. Please start again.
Okay. It's a DSLR single frame image of the lunar eclipse. I just played with the aperture and shutter speed so it would look similar to what I was seeing naked eye. And that's all for me.
Thank you, Stephen. Ah. There we go. Paul Osmond.
Thank you. So on March 14th, I stayed up for the whole lunar eclipse from about 12 a.m. to 4:30, and that was a long, cold night. And so basically, I used a DSLR and a Dobsonian telescope, an 8-inch. So these are unstacked; they're just single images, and they. I was playing with the ISO and the exposure time as the night went on. So this is just before it started. This was around 12 o'clock. It's obviously still a full moon at that point. It's working.
Yeah, that one.
That one there?
The green one.
There we go. Thank you. So obviously now this is getting close to half, and so again, still my ISO at this point. Sorry, I forgot to mention the previous one was ISO 100 at 1/400th of a second. So now the moon is getting darker, and I'm starting to drop my exposure time. So this is 1/320th of a second, and again trying to keep the highlights from being blown out. Same kind of thing here. Now this is probably what 85–90% close to covered, and I started to increase the ISO, and I dropped the exposure time to 1/25th of a second. Again, the idea is to try not to make all this area, the bright area, go white. And next. So at this point now, we're getting pretty close. This is probably about the 90% phase. So this is probably close to 2:30 in the morning, maybe 20 after 2, give or take. And at this point, I didn't care about the bright parts now. I wanted to start to see the more shadowed area. So my ISO went from, or I put my ISO at around 1600, and this is 1/50th of a second. And, whoops, next. And this is totality here. So this is approximately 2:30 in the morning. And again, I did this image with the idea of, you know, my ISO to bring out the nice red color there, right? So, and this is 1/30th of a second. So next. And this is my acquisition. So this is my 8-inch Dob. My DSLR is right here. It's a Skywatcher 200p flex tube. It's an f.9 scope, 8-inch. And my, it's just a T-ring adapter there, and my, I just had prime focus. So next, and you can see the moon is starting to show shadow up there. And this is my DSLR connected directly into a focus tube. It's a Nikon D7500. It's a full spectrum modified camera. So there was a filter, and the filter was my ST Optics Nightscape filter, which is essentially a UV IR cut filter with some light pollution added in for contrast. I have a little red dot finder there, and again, I mentioned the 2-inch T adapter, which connects it in. And so I stayed out for the whole night, and if you do that, you can put a nice, pretty picture together like this. So that's the close to the start. So it goes this way, almost to totality. This is totality here and here. This is just to balance out the image. And again, so when I mentioned the ISOs and the exposure time, so you keep increasing the ISO and dropping the exposure, and then you reverse the process on the opposite end, right, as the moon gets brighter and brighter and brighter. That's it. Thank you.
Thank you. All right, John. John, all right, there you are. There you go.
I've used a series of pictures that I took on evening of March 23rd, and it's demonstrating a few new features that have been added to the C-Star, the ZWO device that I bought about a year ago. This is the well-known double cluster, but what I've done, I've used a new framing feature because before that, it would have been difficult to get those two objects in the same field of view. They would have been tilted at about a 45-degree angle and a very tight, but using software and firmware, I could rotate the image so that they line up properly. And so they fit, will expand to the size of the field too, so it fit better. This is, again, a pair of galaxies it's just off the bowl of the Big Dipper. And these are two of the brighter galaxies that if you have high power binoculars, you might be able to see them, but it makes a nice pair also in the sky. Now what I've got here is, I've got two images of the horse head. This is a before and after. This is actually the after. And you can see here, that was only an 11-minute exposure, so I was surprised at what I got. Oops. How do I go back? Okay. Okay. Is that, oh, I guess I want to go. Okay. Okay, that's the after it was processed. There was the way it came out of the camera directly. After 11 minutes, you can see it's quite grainy. But I applied a new feature called AI denoising, artificial intelligence denoising, that common denoising programs that remove grain will also kill all of the faint stars if you use it. But this one is intelligent enough that it can pick out the faintest stars and hold on to them while it gets rid of the grain. So just, oops. So there it is afterwards. So comparing the two of them, it has the effect of reducing or actually increasing the exposure effectively by about a factor of 4 or 5. Or in other words, it would take like a 45-minute to an hour exposure, not denoised, to get that image that I actually got in 11 minutes. So that's quite an improvement. I was quite surprised at that. And I saw the same effect when I did the California nebula a few months ago. Okay, there's the grainy version again. And then finally, my last image was the M42, the Great Orion Nebula. Now, Orion is just starting to fall into the twilight now. It's going to be hard getting it into dark skies, but anyways, that again is a 5-minute exposure, and I was quite pleased with that. So that's it.
Thank you, John. Jim, there you are.
So I'd like to say that I was like Paul, who mentioned earlier that he was up for the entire eclipse, but I wasn't. I was up for brief moments in time to check my automatic rig was working away, and then I would go back to sleep. The image on the left is sort of from the beginning of the evening, showing the shadow just beginning to cover the moon. These were all taken using a planetary camera on a 4-inch refractor. The ASI 585 was the camera. And they were 1,000 frames that were then processed later, stacked and sharpened to give the nice detailed image that we see here. So image on the left, like I mentioned, it was around the start of the penumbral stage. And then the image on the right is around when the maximum eclipse occurred. I had it around 250, but I might have been off for a bit. This was my first experiment using a feature in SharpCap. I don't know if anybody uses that free software, SharpCap. If you get the purchased version, there's a feature called feature tracking. And what it allows you to do is the software will control your mount, and you just say, okay, I want you to follow this feature. and it will move your mount automatically to keep that object in the field of view and allow you to go have a nap. And it worked quite well until the moon got really dark. And then it kind of said, I don't know where the moon is anymore, which is why I got up about every 20, 40 minutes to make sure it knew what it was doing. Anyway, it was a reasonably good success, and I recommend you to check it out if you're interested in doing long period of time imaging of especially the sun. It'd be excellent for tracking the sun. Anyway, so that was my lunar. It was a beautiful night, by the way. Beautiful night if anybody was out. Nice and warm. A rarity these days. So this was later in the month, the night of the 19th. One of the rare nights I had to do any deep sky imaging over the past month. This was a brief 2-hour session that I had before clouds rolled in from my backyard. Galaxy season, of course. I like going for groups of galaxies. So M105, which is the really bright galaxy here, is quite close in the sky to a number of other galaxies there, NGC 3384 and 3389. So that fits nicely into the field of view of this is a 10-inch RC with a DS432 monochrome camera from Mellencam. 20-second sub-exposures stacked for about 10 minutes, about 30 frames. Another cluster down here, commonly known as the Leo Quartet, but also known as the Hickson Compact Galaxy Group number 44. I look for Hickson Galaxy groups. There's many of them in the spring sky, so they're worth hunting for and checking out. And then a couple of spiral galaxies. 2903 I found to be pretty cool. Neat extended spiral arms on it. The face on spiral NGC 3344 is also pretty neat. I don't know if you can tell. Great, I can see it better on the monitor here. These two galaxies are actually interacting, and there's a bunch of material glowing up here that's tidally removed from one of these two spirals. So that's an interesting galaxy pair to check out. It's also in Leo. And then finally, in the bottom right corner was the observing target. I believe it was the most challenging one, NGC 2775. That was for the month of March. One thing that I came across in processing these images was a new feature in a program called raw-RASC. If you haven't heard of raw-RASC, it is a free downloadable software that you can either plug into your PixInsight or you can use standalone. I use it as standalone, and you can kind of see what it is able to do. The image on the right is the raw stack of 30 frames out of my camera. The middle image is what happens when you use it to remove the background or the gradient. That's why it has its name, Gradient Expert. Plus a 10% stretch, and then it now has quite good AI noise reduction, which is the image on the right. So I was pretty pleased with that, considering it took me all of about 2 minutes to do. Anyway, so very useful tool. And the AI is constantly being improved over time. And I believe this is my final image. It's from the 23rd. I did get out. It seemed like we had a lot of sunny days, but not a lot of clear nights in March. So I took every opportunity to do some solar imaging when I could. This is from the 23rd. The image on the left is from my spectroheliograph in calcium 2K. And on the right is with my, my double stack hydrogen alpha setup. Both on the same telescope, both the same camera, just different ways of filtering out the sun's light. One of the things that I find super impressive about the calcium K image is, if you notice this right here, is that. This over here is this. This down here is this. So in the calcium K image, you can actually see filaments, which is something that you absolutely cannot do with a conventional calcium K filter. So +1 for the spectroheliograph. And I will share more of my excitement with the spectroheliograph in June, I think, when I'll give a talk about it, how it works. That's it for me, I think. Thank you.
Super. Thanks, Jim. That sounds very cool. I haven't heard of that program. I'll definitely give that a try. That looks like a worthwhile pursuit. All right. Hello. Taras.
Hi everyone. So 2024 was good year for planets, and we're still at last probably glimpse of the season when you can image Jupiter. It was quite high last year, and it's still high before sunset. But unfortunately, within the next few months, it's going to be getting closer to sun, and we will not see it until late 2025, this year. Good news that by the end of this year, it will reach almost 60 degrees altitude. So it's going to be up, and that means that when you look at it through the telescope, you will see probably more details because it will be less susceptible to the effects of bad seeing. So this image taken on March 8th was probably my last take on Jupiter. I used LRGB, which is a standard set for filters used with the monochrome camera. And I also added some infrared data to highlight the bands a little bit better. I'll show it in the next slides, how it works. As for Mars, it's getting further from us after it was at the closest, or rather at the opposition in late fall. But these are seemingly different sizes, but the size of this one was 10 arc seconds, and this one was 9.4, 9.7. So the difference in sizes visually now is due to the fact that they were taken with two different telescopes of different focal length. So for the one with more details, obviously the larger telescope, or rather larger aperture was used, and it allows for more details to be shown when you image it. Of course, the seeing does matter as well, but with comparable seeing, so this was with my 8-inch Newtonian on March 13th, it's about the same phase because the rotation of Mars is about the same as Earth, closely around 24 hours. So when we image about the same time, we see about the same phase. As for Venus, right now it's a really great time to get to see it because it just passed from being set right after sunset, or right, so it would set before sunset a month ago, and now it's rising quite early. So the inconvenience is that we have to see it around like 5 o'clock, 6 o'clock a.m. rising, but it's really big. It's, if I'm not mistaken, 50 arc seconds diameter. So you can see how this was still back when it was on the other side of the sun with reducing crescent. And as it gets closer to the sun, it slightly increases in the visual diameter, but the size of crescent gets thinner and thinner. So right now it's on the opposite side. I haven't prepared the pictures of it yet, but probably next meeting I will show you some of Venus as well. So this is actually was inspired by Jim's and Paul's talk last month about the infrared imaging. I did some tries before, and actually I'm using it quite often to add some details to imaging, like with this, for instance, with the Saturn image. It's a bit strange for Saturn because you see it's quite different from what you see visually. The rings are much brighter. There is much brighter infrared data coming from around equator area, but it still can be used if you mix it with one of the color channels that just to reduce the noise. Jupiter also you can see similarly to what Paul was showing, if I'm not mistaken, with the brighter areas on the both poles. So this is not what you usually see visually. It was also interesting that the moons, they shine much brighter than in comparable visual imaging. And Mars is surprisingly looking the same way, almost the same way as you would see it in visual range, probably because it reflects infrared light, but the same proportion as visual. So this, sometimes I'm mixing the infrared with just a red channel for Jupiter images. So it gets, it shows more details and highlights the bands more clearly. Same infrared camera, infrared filter with a planetary camera was used for imaging some details on Moon. So if I'm not mistaken, this is Mare Imbrium with Apennines Mountains here. Again, as Jim mentioned last meeting, it provides incredible amount of details, even during bad seeing. So this is the example of that. And as for the eclipse, I waited until almost 3:30 or almost 4 o'clock, but not the whole cycle that night of the eclipse. What's interesting is that the shadow was, or usually is, 3.6 times larger than the diameter of the moon. So you can see the shadow probably would go around like this. So this is collage, obviously. It's not what the sequence was in terms of the positions, but I positioned them such a way that it would reflect the shape of the shadow. And this last lunar eclipse was such that the edge of the shadow over here would practically touch the edge of the moon. So as you see, this part, even during totality, was slightly brighter, which is quite noticeable on this picture, while the bottom closer to the mid of the shadow is darker. And the close-up of totality with, this was 10 pictures taken as a sequence, as a batch around 3 o'clock, 3:03 if I'm not mistaken, with them being stacked and later processed with Photoshop and yeah, just with the Photoshop. If you notice this feature here, so the next slide, when you'll see the video sequence, it will be 90 degrees rotated because of the position of equatorial mount. And the feature is over here. So you can think that the bottom is actually this way. But if you can play the sequence, let's see. Oh, right. So that was shadow incoming on the ingress. This is moment of totality. And the shadow retreating, uncovering the other side. I didn't wait longer, so this was the end of it. Thank you.
Thank you, Taras. Nice imagery there. Oh, that's me. All right. Like some of the other diehards, I was up for the entirety of this event, and this was an interesting eclipse for a number of reasons. I'm going to show you this little animation first because you may have noticed in some of the images you've already seen that, or if you made visual observations yourself, that if you were expecting a blood red moon, which is very common, the term that's very commonly heard for total lunar eclipses, that's not what we got this time around. And this animation will make it obvious. This was actually a very shallow eclipse, shallow in the sense that it passed into the Earth's umbra, giving us a full lunar eclipse, but it never strayed very far from the edge of the umbra. In fact, the farthest it ever got from the edge of the umbra was 5.5 arc minutes, which is only about a sixth of its diameter. So as Taras was alluding to. It stayed close to that edge, and that had some interesting ramifications on the on what you saw there. So I'll let this run. That first arc is the edge of the penumbra, the partial shadow of the Earth. This one coming up is the umbra, and anything within that is within the full umbra. But watch how the top edge, the top left edge of the moon, stays fairly close to that umbral boundary. Even at maximum eclipse there, you can see that it's fairly close. And then leaves the umbra, and you get your partial eclipse on the one side, and as it leaves that, we're left with the umbral eclipse. So yeah, if you were expecting a deep red one, that's not what you got. Interesting. Although the cameras will record it, the cameras will record a much deeper red there. But this is very similar to what Tara showed you. I tried to process my images to match what I was seeing. I also had my 25 by 100 binoculars out, and it was just an awesome view. We really lucked out with this one. I mean, the night was clear throughout, except for the last stages near the end of the partial eclipse. But for most of the rest of the night, the air was stable. The sky was clear, and the moon was really nice and high in elevation. We're talking over 45 degrees of elevation, which again lets you look at it through much more stable air, and if you're doing imaging, allows you for much crisper images. So I had two scopes running. I had my 11-inch running because I wanted to get some high resolution views of the eclipse, and I also had my 82 millimeter Evolux running to get a wider field view, which is what that came from. I'll show you the 11-inch sequence first. This is not a video sequence. It's just a sequence of 10 images at various stages through the eclipse. I just picked them out just to highlight it, and you'll be able to see the progression of the moon through the shadow and how that light area at the northern part of the moon migrates down counterclockwise along the rim as the moon moves through the shadow. It does get darker down to the southern part, which is closer to the center line of the shadow. There's maximum eclipse, and see how bright that edge still is. That's very much what it was visually as well, even though this is in the full shadow of the Earth. Totality ends, and now you'll see that area grow as the moon moves out of the umbral portion of the shadow into the penumbral portion. Interesting thing to watch, though. You really got a feel for it with the fact that the moon was up near the edge of the umbra. You got a feel for how that shadow was rotating as you watch it through. So that was with the 11-inch, and as I mentioned, this was with the 82 millimeter. This was a collection of continuous images, although I did have a couple of breaks in the sequence, one due to a battery failure and another one due to a bit of a glitch with the mount there. Anyway, I stitched them together to give you an idea of the flow of the eclipse. So this is from about 1 till 5 in the morning, and it just goes through various stages. Change the exposure of the camera so that collect the shadowed part there. There's the beginning of totality. Watch the migration of that bright part counterclockwise as this progresses. There's maximum. There's the end of totality. And there you can see where the moon starts to leave the umbral part of the shadow. Here's my break, and I resumed it, but just towards the end of totality. I thought this was kind of neat, though. The thin clouds were moving through, and so I didn't really mind it. It wasn't at the middle of the eclipse, and of course, then I ran into some trees as well along the way. Yeah, go figure, right? So just oops. I hope you enjoyed this. For those of you that got a chance to view this or image this, this was actually a pretty special eclipse for a couple of reasons. We had clear sky. How unique was that this winter? The second being, this eclipse, as I mentioned, was at about, I think it was 47 degrees elevation at its maximum height. We don't get another total lunar eclipse in our area at that high elevation until the late 1940s. So we've got a bit of a wait. It's not as high as this, not in our area. What, I'm sorry? 1940s. Oh, I got into a time warp, the 2040s. I stand corrected. Thank you. Hate those time warps. Anyway, yes, until the 2040s there. So we've got a bit of a wait for another one. As Jim mentioned, the benefit of the higher elevation is the fact that the air is more stable, and visually you get less interference from seeing, and photographically it makes it much nicer to take images. I think the next nearest one is in 2047. It only reaches about 37 degrees at maximum elevation from our area. And then in 2049, it actually exceeds this one. And I think we're at 52.5 degrees. So I hope to be around to see that one. You and me both, right, Dave? All right. So my last one is just an image that I added in the last minute. This was taken Tuesday night. The sky was hazy, but the moon was close to the Pleiades, and I thought the halo effect made for a neat shot. And we got the Pleiades just down into to the right of the moon itself. So kind of a clear night, sort of, kind of, sort of. All right. Hey. Thank you. And Richard Taylor. Richard, show us his observations, and then you can jump into your observing challenges. There you go, sir.
Thank you. Okay, so the challenges for this last month were in the constellation of Cancer, and that's my first observation here. I wanted to get a picture of Cancer, and I was just using my little M100 mirrorless camera. But the night I chose was particularly bad. It was the night of March 11th, and there was a gibbous moon just off to the lower lower left down here. And it just swamped the picture with glare and even an internal reflection. I thought, oh, this is not going to come out very well. But the magic of post-processing, it really saved me on this one. I was quite happy to find that just by using the StarNet plugin to PixInsight, I was able to pull out just the stars. And of course, there weren't any nebulas to be found in Cancer, but there is the nice beehive cluster right there in the middle. So it worked out very nicely for me on this. So there's my picture of the constellation of Cancer. Now, when you do get a long exposure like this is not very long. What did I use on this one? I think this was a 6-second exposure, but you can still get a lot of stars using a regular camera like this. And as I say, the StarNet takes away all of the sky glow, all of the glare from the moon and everything else. So you can get nice constellation star pictures from the city with a lot of light pollution. So here's the outline of the constellation. It's a fairly faint constellation. The stars are around 4th magnitude. So it's not an easy constellation to spot, except for the beehive right there in the middle. And another interpretation of this particular section of the sky was that it's 2 asses eating from a manger. So this was known to the ancients, and it was, quite an indicator of the spring when you start seeing Cancer in the sky in the evening. Zooming in on the beehive cluster, this is now using my refractor. M44 is a wide open cluster. It looks great in binoculars, but it's not very dense. There's a lot of interesting colors involved in some of the stars when you look at it on a telescope or if you take a picture like this. But the cluster itself is not particularly dense. The next challenge object is Messier 67. And it's a much denser and more interesting cluster, I think. But I've zoomed in now with the planetary camera so that you can see it about the same size on the screen. But it is a much smaller but much denser cluster. It's also known as the Golden Eye cluster because of this one golden star that stands out above all the rest. So this is a stack of 57 30-second exposures. Now the next challenge object was a little galaxy, NGC 2775. And this was quite a bit of a challenge. The center part of the galaxy is quite bright, but it's what's known as a flocculent spiral, meaning that the spiral arms are not very distinct as arms. They're sort of mottled. I think I managed to see it. If you look really closely on the original image, you can sort of see that mottling, but it's really not very easy to see. However, I was happy to find that there were a couple of other little galaxies nearby, NGC 2777 and 2773. So this is a sign of the galaxy season to come. You get more galaxies when we're looking out through the thickness of our Milky Way rather than looking into the center of it. Oh, I forgot to include my lunar eclipse picture. I did get one. I woke myself up at about, was it no, a little bit before 1:30 in the morning, and I stayed out until about 2:30, and then I said, that's enough, I'm tired. So I did not get a sequence. We did see quite a number of different observations of the eclipse on the Discord server. So gold stars for the people who managed to capture them. Jim Thompson also had some pictures of the constellation, Beehive, and M67. Lots of pictures of the lunar eclipse. And a special shout out to Andrea Gironis, who got not just the lunar eclipse, but she also got the solar eclipse, which here in Ottawa was clouded out. What was it, New Brunswick, Andrea? Oh, she left already. Okay. Anyway, she got a lovely picture. It's on the Discord server. You should take a look at it because she got photobombed by a bird flying across the solar eclipse. It's a lovely picture. Okay, for this next month, it is galaxy season, and a beautiful place to look for galaxies is in the constellation of Coma Berenices. Once again, I'm following my theme of very faint constellations this year. So the actual constellation itself is pretty difficult to find. You've got the 3 stars here, just behind the tail of Leo. Denebola is the tail of the lion. But in a very old version of Leo, there's a tuft on the end of Leo's tail. This collection of stars now, and it's now part of Coma Berenices. In fact, it's really the main element of Coma Berenices, Berenice's hair, basically. But it's a cluster. It's an open cluster of stars, now known also as Melot 111. It's quite easy to see if you're in dark skies. If you look for the tail of the lion and look up and to the left a little bit, you'll see this lovely tuft of hair. And it's even better in binoculars, of course, but not very high power. It's a big cluster. So that's your second challenge, level 2 challenge. And then there's a particular galaxy, or what we, oops, I'm looking at the wrong notes here. M100. So again, just a little bit down from the tail of the lion. M100 is also known as the blow dryer galaxy, and it's quite a lovely spiral galaxy. So you should be able to see that in a telescope or get images of it. It's also around a lot of other galaxies down here, but the main place to look is our level 4 challenge, the Coma Galaxy Cluster. Up in this region here, there are lots and lots of galaxies. They're all pretty faint, very small, but it's a lovely place to cruise around at high power or get a picture of this group of galaxies. So those are the challenges for this month: the constellation Coma Berenices, the Coma Star Cluster, or Belot 111, the blow dryer galaxy Messier 100, and the Coma Galaxy Cluster. For the solar system challenge, I thought it was time to have another lunar challenge. And I was reading that the libration of the moon is particularly great at this particular time. The moon is extremely high in the north right now, so it's almost overhead. If you look out tonight, if it's still not cloudy, you'll see it way up high. And the interesting thing is this brings around some of the southern and eastern features on the moon that sometimes are not visible at all. But right now, the libration of the moon has pulled them around, so you should be able to see a feature called Mare Austral, the Australian Sea, or the Southern Sea on the moon. So take a look at that. It's surrounded by a number of flooded craters, and it's right on the southeastern edge of the moon right now. I got a picture of it last night, in fact. I was taking some pictures through the clouds, and it's definitely quite easy to find right now. So let's see if you can do those challenges for this month. Thank you.
Thank you, Richard. Excuse me. All right, Estelle is with us this month, and again, she's recommending The Modern Moon, a personal view by Charles A. Wood, who for many years ran the lunar photo of the day, I believe it was, website there. So a man very experienced with lunar observations and lunar imaging. Fred Lossing Observatory, just a reminder that available to us, now becoming less and less snowed in. I know Taras and Andrew had a bit of a challenge with FLO trying to get to there, use it as an eclipse site, but yeah, well, you all know the weather we got around that time. So that's much less of a challenge now, and it is accessible. For members, the scopes are out there, the 3 observatories that we have going, and so we hope to see a lot of use of that in the coming months. FLO Star Parties, the next one being April the 26th. Cross our fingers again and hope for some clear sky. And this is a members only event, so just to let you know. Just general club information. The director of FLO, if you have any questions or comments that you'd like to direct to him, is Rick Scholes. Estelle, as I mentioned, is our librarian for the Stanmont Book Library. Peter Shute is in charge of the Ted Bean Equipment Loan Library. As I mentioned earlier, if you're interested in borrowing a scope or even just finding out what we have, you can contact Peter. And we have, if you have any inquiries about your RASC membership, please contact Art Fraser. All right, tonight we had 55 here, 35 at Zoom, so 90 folks. Thank you again for all the contributors tonight with your raft of images. That was excellent. And if you have any comments about our meetings or ideas, I am looking for presenters for the coming months. So if you have something that you would like to share, piece that interests you and would like to create a presentation, if you need a hand with that, you're certainly welcome to contact Chris and myself. And we'd be more than happy to help you with that if you've not done that before. Same goes for the Shorter's Astro Bits segment. If there's something that's really caught your eye there and you figure you can pass on that interest in a few minutes discussion, again, please give me a shout and we'll get that going. So thank you very much. The post-meeting meeting, for those interested, will occur at Liam McGuire's down at 1705 Saint Laurent. And our next meeting is scheduled for May the 2nd. So same time, same place, May the 2nd. Hope to see you all here and wishing you clear skies for the month. Have a good evening.